So we've looked at what to do when we have three charges in a row. You have two charges, it's easy, right? We want to find the force between them. It's just simply Coulomb's law, F is equal to K, Q1, Q2 over R squared. It doesn't matter which one is Q1, which one is Q2. The big thing there is don't forget to square R. Don't forget to square the distance that separates them, right? What if we have three charges? We talked about that a bit yesterday. Let's make the first one positive, the second one negative, and the third one negative. Okay? Let's make the distance between them 1.0 meters just for simplicity. And we're not even going to assign a value to the charge here because I don't want to bother going through the process of calculating the values of the force, just the process of how we would calculate the values of the force. Let's say we want to find the net force, first of all, on charge number 2. So we want to find the force on this guy right here, charge number 2. First thing we got to do is what? We have more than one force acting on charge 2, right? There's the force of 1 acting on 2 and the force of 3 acting on 2. So what are we going to do? Whenever we have 2 or 3 or 4 forces acting on an object, whether it's a Coulomb's law problem or a inclined plane problem from physics 20, what do you do when you have more than one force acting? 3 words. Free body diagram. Draw a free body diagram. So we have the force of 1 acting on 2 and the force of 3 acting on 2. When you're finding 1 on 2, let's pretend 3 isn't even there. Okay, let's cover it up here. 3 doesn't even exist right now. We want to find the force of 1 acting on 2. Which way does 2 move as a result of that force? Is it pushed to the right as a result of number 1, or is it pulled to the left as a result of number 1? It's pulled to the left. It's attracted to number 1, right? Now, we know that 1 is attracted to number 2 as well. 1 is pulled to the right. Correct? But do we care? Not right now, we don't. Okay, if we're trying to find the force on number 2, okay, which direction number 1 is pulled is completely irrelevant. Now, let's pretend number 1 isn't there. Let's look at the force of 3 on 2. Is 2 pushed away from number 3, pushed to the left, or is it pulled to the right as a result of number 3? It's pushed to the left. Why is it pushed to the left? It's a repulsive force. Negatives repel negatives. Now we know that number 3 is pushed to the right. It's pushed away from number 2, but we don't really care right now because we're trying to find the force on number 2. So this is the force of 1 on 2. This would be the force of 3 on 2. Now we've got to calculate both of those forces. That's easy enough. KQ1, Q2 over R squared, KQ2, Q3 over R squared. Then we got to add them up. When we add them up, what do we got to pay attention to? We're adding those two forces. We're going to make them both negative in this case, right? Now, technically, because they're both the same direction, you could make them both positive if you wanted to, as long as you recognize that positive was left in that case. Bottom line is they've got to be the same sign. They've got to be the same sign because they're both in the same direction. All right, let's change the question around a little bit. Let's say now we're trying to find the net force on number 1 instead of on number 3. There's a force of 2 on 1, and there's a force of 3 on 1. Which way does 2 act on 1? Now, is number 1 pushed away from number 2, or is it pulled towards number 2? It's pulled towards it. Now we care what happens to number 1 because we're trying to find the force on number 1. The force of 2 on 1 is to the right. Do we care what happens to number 2 this time? No, that was the last problem. Now we care what happens to number 1. Okay, let's find the force of 3 on 1. Is there a force, by the way, of 3 on 1, even though 3 is way over here? Sure there is. Sure there is. If you have a charge on the other side of the universe, there's a force acting on number 1 as a result of that. Now, we wouldn't pay any attention to it because it would be such a ridiculously small force that far away that it wouldn't matter. Okay, but this one's certainly close enough to matter. Force of 3 on 1. Does number 3 push number 1 to the left, or does it pull number 1 to the right? Okay, remember, we're pretending number 2 isn't there right now, right? 2 doesn't exist as far as we're concerned right now. 3 does what to number 1? It pulls it to the right. So we're going to say F31 is a force to the right as well. Let's calculate both of those forces. KQ1, Q2 over R squared, KQ2, Q1, Q3 over R squared. And then we're going to add them up. When we add these two guys together, we're going to make sure that they're both positive numbers because they're both to the right. Does that make sense? What's R going to be What's the value of r going to be when we're calculating the force of 2 on 1? What's the value of r? 1 meter. Don't forget to square that, although if you did forget to square it in that case, you'd get away with it, right? Because 1 squared is still 1. What's r when we're talking about the force of 3 on 1? It's going to be 2 meters, right? And it's a lot more important to remember to square that one because 2 squared is 4. Why is it 2 meters, sorry? Because we're not just taking a random number, we're taking the distance from one charge to the other. The distance from charge 1 to charge 3 is 2 meters. Okay, is that good? All right, let's take a look at the homework that we had last night, page 533. Number 1, I think, was relatively straightforward. Number 2, I think, we probably found was a little bit of a challenge question. Agree? Okay, so let's take a look at are we good with number 1, or do we want to go over number 1? Anybody need to go over number 1? Okay, let's take a look at number 2 then. It is definitely a challenge question here. It says we've got 3 charges here. We want to know where the second sphere needs to be to make the net force 0. So let's draw this out. Here's charge 1. Here's charge 3. Charge 1 is negative 2.5 times 10 to the negative 9 coulombs. Charge 3 is positive negative 1.0 times 10 to the negative 9 coulombs. And we got a charge 2 in here somewhere. We don't know where it is, but it's somewhere in between 1 and 3. It's positive 1.5 times 10 to the minus 9 coulombs. We've got 1.50 meters here, or centimeters, which gives me 0.015 meters. No, we don't. No, we don't. We know the only thing we know here is the distance between 1 and 3 is 0.035 meters. Right? We don't know where number 2 is. We know it's somewhere in between there, and we know that 1 and 3 are 0.035 meters apart because in question number 1, that's where it was. Does that make sense? Is that diagram okay so far? Is there anyone puzzled about where we are? Because we can't move forward if you don't understand, say, that distance of 0.035. We want to find where number 2 is. So we want to find this distance right here. Okay? We don't know what it is. We want to find it. Well, what do we know if the net electric force acting on number 2 is 0? If the net electric force, the net force of any type acting on an object is 0, then we know whatever forces that we have must be equal. They must be balanced. They must be equal. So there's a force of 1 on 2 that's to the left. There's a force of 3 on 2 that's to the right. And we know those two forces must be equal but opposite. So I'm going to say the force of 1 on 2 is equal to the force of 3 on 2. Technically, the forces aren't equal because one's a negative, one's a positive, but the magnitudes of them are equal. Yep, Travis? It's 3.5 centimeters. No, 0.35 would be 35. 0.035 would be 3.5. Yep. Yeah, divide by 100, right? Okay. Good? Okay, so the force of 1 on 2 is going to be K, Q1, Q2 over R squared. The force of 3 on 2 is going to be K, Q3, Q2 over R? No, it's not R. It's not R. What's the distance between 2 and 3? Good. 0.035 minus R. Now that looks like an ugly equation here. 0.035 minus R squared. It is kind of ugly. But that's what the distance is. Remember we talked about variable value changing? With variable value changing, the equation for momentum was was mass times velocity. Not m times v, it was mass times velocity. We just represented the mass by the symbol m. Okay, then sometimes we represent it by 2m if we double the mass. Well here, again, the distance isn't r. We just represent it by r, usually. Here we're representing the distance as 0.035 minus r, not r. Okay, we can simplify this a little bit. K appears in both terms, cancel it out. So does Q2 appear in both terms, cancel it out. So we're left now with Q1 over R squared equals Q3 over 0.035 minus R squared. This doesn't look like it's going to be pretty. Q1 is 2.5 times 10 to the negative 9. Remember, we're dropping the sign of the charge as we always do when we plug it into an equation. Q3 was 1.0 times 10 to the minus 9. Wow, what do you want to do to solve for R? Listen, if we solve for R, we're done, right? Where is charge 2? Well, it's this far away from charge 1, whatever R is. There's only one variable in there that we don't know. So what are you going to do to solve for R? Man, it looks ugly. Sorry? Cross multiply? Okay. William, what were you going to say? Okay. We don't actually have to cross multiply yet, but eventually we're going to have to, so we might as well do that now. What I was thinking was actually something else first, but we'll go with what you're going here because in the end it's going to be the same amount of work, whatever order we do it in. Let's make that 2.5 times 10 to the minus 9 times 0.035 minus R squared equals 1.0 times 10 to the minus 9 times R squared. Is that good? Oh, you know what I just noticed? I don't know how many of you guys noticed this, but can I do that? I can cancel out 10 to the minus 9, right? That's not really a big deal, but it saves us a little bit of bother in our calculators, right, to not have to worry about those exponents. Honestly, I just noticed that, okay, when I was looking at this question. That didn't occur to me until just now. Oh, what now? Oh, goodness. You know what my first thought was when I saw this? My first thought? It's a word that you don't like. FOIL. Right? FOIL. First, outside, inside, last. But then it occurred to me, wait a second. There's a much easier way to do this than to FOIL it. Anybody see it? Take the square root of both sides. Square root of both sides. What's the square root of 2.5? Somebody figure that out, please. Square root of 2.5. Okay. So we got 1.58 times 0.035 minus R. The square just disappeared. Equals, well, the square root of 1 is 1 times R. Well, now it's looking a lot better. Still not pretty, but it's looking a lot better. Okay, let's distribute the 1.58. Okay, what's 1.58 times 0.035? 0.055, thank you, minus 1.58R. Right, I'm multiplying 1.58 by everything inside the brackets. Equals 1.0R. Let's take the 1.58R over to the other side by adding. No, it's subtracting 1.58R on the left side. So if we want to take it to the other side, we're going to add it. So it becomes, what's 1R plus 1.58R? 2.58R. So R is now going to be equal to 0.0553 divided by 2.58. What's that equal? 0.0214 meters. 0.0214 meters. So my distance now, the position of charge 2 is 0.0214. That's 2.14 centimeters to the right of charge 1. I'm curious, did anybody actually get that? Yes, good. That's a tough, tough question. Guys, listen, this is one of those questions that we do because it's good mental exercise. You will not get a question that's that difficult mathematically. Okay, the idea of setting those two forces equal, absolutely, that's fair game. Okay, the idea behind this question, the concept behind this question is absolutely fair game. But you won't get a question that's that difficult mathematically. Okay, sometimes they can be mean, but they're not that mean. Okay, if they're mean, it's usually physics mean, not math mean. Okay, and this is a math mean type question. Okay, but you know what? Just like, listen, just like when you're training for the big game, you're training for in a certain sport, whatever, for the big game. Sometimes you train harder than you actually have to play. Than the game is actually going to be, right? And that's what we're doing here. Okay, this question is training harder than the game, so that the game becomes a little bit easier. Yep. Um, how do you know which charge it has to be more to the right of? As opposed to this one right here? As opposed to this distance? Well, we could have found that distance. We could have called that R. If we had to call that R, then this would have been 0.035 R. What do you think we would have gotten if we had to solve for that distance? Well, we got 21 centimeters here. We would have gotten 14 centimeters. And that would have been a correct answer. 21 centimeters to the right of charge 1 or 14 centimeters to the left of charge 3, both of those would have been correct answers. Okay. I don't know why I picked that one. When you look at the answer, that's the one that they picked as well, but both of them would have been right. Good? Okay. Well, if you guys feel okay about that, let's take a look at 10.5 on 534 here. Here's a small metal sphere A with a negative charge that's to the left of another one. So here's A to the left of B. This one is negative 2.10 times 10 to the minus 6 coulombs. It's 0. Let's just say 2 times 10 to the minus 2. Okay, so far, so good. That's easy enough. This charge is 1.50 times 10 to the negative 6 coulombs. Okay, easy enough. The third one is below sphere B. Oh, that's not looking good. It's down here. The distance is 3 times 10 to the negative 2 meters. And that charge here is 1.8 times 10 to the negative 6 coulombs. On first glance, this doesn't look good. But if we stop and take a step back from it for a second, this is not a hard question. I'm confident, actually, that there's a number of you that could probably do this question right now before we even looked at it. How do you think we'd go about it? Go ahead, Travis. Find the angles. Okay. Find the distance between A and C. You could, but you don't need to, actually. No, you don't need to do that. Don't need to. Patrick? Okay. Okay, so let's get that free body diagram drawn. The force of A on B is to the left. A pulls B to the left. That's my fab force. The force of A on B, my fab force. To the left. Now A would be pulled to the right, but we don't really care what happens to A right now. What about my force of C on B? Well, they're both positive. So C on B is going to be upwards, right? That's my fab force. This is my force. FCB, the force of C on B. It's upwards. Let's get the values of both of those forces. Let's say FAB, my fab force, is KQAQB over R squared. It's 8.99 times 10 to the 9 times 2.1 times 10 to the minus 6 times 1.5 times 10 to the minus 6. Divide it by 2 times 10 to the minus 2, and we can't forget to square that. It becomes a little bit ugly with that exponent there. What do we get when we do the math on that one? 70.77965, thank you. Okay, let's get the force of C on B then. So far, this is identical to the questions that we did for homework, right? Identical. I haven't changed a thing yet. I mean, look at the forces, they're different directions, but homework questions, they're different directions too, just not right angles to each other. The calculations are certainly no different. So here we've got 8.99 times 10 to the 9 times QB, which is 1.5 times 10 to the minus 6, times QC, which is 1.8 times 10 to the minus 6, divided by the distance of 3 times 10 to the minus 2, 26.97 newtons, thank you. Now what? Now is where it becomes a little bit different. If this was the questions that we did yesterday, we would have said, okay, we add the forces together, right? Just pay attention to signs. Now we're still going to say add the forces together. But now we have to add them together vectorially in 2 dimensions. And how do we do that? It's a physics 20 problem, right? How do we do that? Sorry? Vector diagram, right. We've got a force to the left that's 70.79 newtons. We know that it's to the left because that's the way we drew it in our free body diagram. We've got a force upwards that's 26.97. We know that it's upwards because that's the way we drew it in our free body diagram. In a free body diagram, doesn't matter where you draw the forces. In a vector diagram, it does. You have to draw them head to tail or front to back in a vector diagram. My resultant vector, which is what I'm really looking for here, is this one right here. It's 26.97 squared plus 70.79625 squared. Square root that. What do we get? 13.607 newtons. We're going to round that to 3 digits, 13.6 newtons. Yes, it should be bigger. Yeah, that's not right. What is it? Okay, that makes more sense, yeah. 75.8. And the angle here would be the inverse tan function of 26.97. That's the opposite side over the adjacent side, 70.79625. What do we get for the angle? That makes sense. 20.9 degrees. We're not going to express that as a north of west or anything like that, because, or a, north of west, because we're not told our frame of reference is north, south, east, west on this, right? It's just a picture to the left, to the right, whatever. So we're just going to label the angle right here as 20.9 degrees. Is that hard? Yep. Would C be attracted to A? Would there be a force of A on C here this way because they're opposite charges? Absolutely. But we don't care about it right now because we're not trying to find the force on C. We're only trying to find the force on B there right now. Okay, now if you're trying to find the force of A and B on C, then that would be a relevant force. Okay, does that make sense? Draw the free body diagram only for the object for which you're trying to find the force. Yep. Yeah, no, absolutely. That's a good point. But I think in one of the classes we talked about that a little bit yesterday. I can't remember which one. The question, if you didn't hear that from Tanner, was, well, as A and C move closer together because they're attracted, then wouldn't that change things? Absolutely. As A and B move closer together, that would change things, right? Okay. What we're looking for here is the net electrostatic force on B when these charges are where they are. 2 seconds later, they may be in different places if they're not fixed to one place. All bets are off then. The force would be different then. Okay, but right now, when they're where they are in this picture, that's what the force is. Does that make sense? Homework for the weekend, everyone? Worksheet number 7. Okay, that's going to give you some questions on 3 charges like this, and it's going to give you some questions on 3 charges like this. Remember, this is the stuff that's on your quiz on Monday. This stuff we'll quiz you on probably Tuesday or Wednesday. Okay? That's it for today, guys.